Hey, welcome back to Principles Engineering. We're going to look at another stress strain calculation in number 6. And number 6 is a three-part problem. It basically says that there's a 100-foot long steel wire with a cross-sectional area of 0.0144 inches squared. And it asks you, when a force of 270 pounds is applied to the wire, its length increases by 3/4 of an inch. So it asks you to determine the stress, the strain, and the modulus of elasticity with different precisions. So what we're looking for here is our stress, strain, and modulus elasticity. All right, so let's take a quick look and make a quick drawing of this. So what I have is I've got a wire attached to some thing, don't know what, but I'm just going to attach it here and pull it down. And what I'd put on the end of it was 270 pounds. And I said that it's 100 feet long. And then I've got basically a delta that it may stretch out to, so it may move down and stretch out here. That's going to be 0.75 inches. So one thing to take note of when you're looking at this is the difference here. So we're in inches and feet. So we're going to have to relate those two to each other later on. So what kind of equations do we need to solve this, or what do we know? Well, we know a few equations from our formula sheet. So let's take a quick look at our formula sheet. So let me pull this bad boy over here. And the first formula that I see is, what's the formula for epsilon? And that's nothing more than my original length divided, or my stretch divided by my original length, my delta divided by my original length. Now notice that's dimensionless, so they need to be in the same units. That's what I was talking about. So we also know what our calculation is for the strain, or stress rather, within the wire, and that's nothing more than the force divided by the area. Now epsilon, the normal strain, is or the modulus elasticity rather, can be represented basically as my, right here, it can be represented as my stress divided by my strain. So pretty straightforward. So let's go ahead and write those formulas down as ones that are going to be handy dandy and we're going to use. So I'll write those formulas down in blue for us to keep track of. So the first one that I said was, what the heck was it? I said that, let's just go here with what my stress is. My stress is equal to my force divided by my area. The second one that I want to write down here is that my epsilon, my strain, is equivalent to my elongation divided by my original length. The third one that I want to write down in here is maybe that my, let's see, modulus elasticity was the third one, is equivalent to the ratio between my stress and my strain. So stress over strain. All right, so I think that'll work out. Nothing really to add there, so let's go ahead and start solving some of this. So let's solve for the first one. And this is pretty obvious. We can get what epsilon is. So let's solve for epsilon. And epsilon is equal to my stretch amount, which is 0.75 inches, divided by my original length, L sub 0, which is 100 feet. Now the problem with this is epsilon is a non-dimensional unit, and in the normal strain, so there is no unit, so I need to get these either both into feet or both into inches. And I'm going to go both into inches because it's pretty easy. So I'm going to go, it's 0.75 inches divided by 100 feet, knowing that there are 12 inches in 1 foot. And what that will do is cancel out my feet unit. So I'll get my handy dandy calculator out and jam those numbers through. And what I come up with is 0.75 times 1 divided by 100 divided by 12. And this equals to point 0.000625. So I carried that out quite a ways. And this is inch over inch, so there's no real units to it. So let's go through and cancel our units and double check that as part of our process. So we see our feet canceled out, and this is inches right here. So now my inches and my inches cancel out. So I think that's a pretty good answer. So what they asked me to answer that question in, though, is they asked me to go ahead and solve for that rounding. So I'm going to round that down to 0.0063. So let me put that down in my final answer. Epsilon equals to 0.00063. No units on it. So that was pretty easy. Let's look at my next one. So I've just done this. So let's look at what my take a look at what my stress is within that. And I'm going to look at the force divided by the area. So I've been given my area, so what I can do is quickly calculate that as my stress is equal to the force, which is 270 pounds, divided by my area, which I can get right back over here, which is 0.0144 inches squared. And that's just a real quick hand jam, so let's do that. 270 divided by 0.0144, and I get the number 18,750 pounds per inch squared, or PSI. Pretty straightforward also, so let's put that down here as one of my answers. E equals to 18,750 pounds per inch squared. Now let's come down and look at what E is. And we've already said from our formulas that, go back to magenta, that E is equal to my stress divided by my strain, my dimensionless strain. So that is going to equal to 18,750 pounds per inch squared divided by my factor right here, 0.00625. And I'm going to use the full one, not rounded, just to make it a little more accurate. So coming back into my calculator, I can now divide my last number by 0.000625. And what I end up with is 30 times 10 to the 6th PSI. So that's my PSI right there. So there you have your E factor, or your modulus of elasticity. 30 times 10 to the 6th PSI. All right, that was quick and straightforward. Hopefully that helped. Thanks for watching.